Previously, we talked about the dot product, which is multiplication with the parallel parts of two vectors, and the cross product, which is multiplication with the perpendicular parts. In this video, we are going to talk about the third way of multiplying vectors, which is the dyadic product. This will be an introduction to tensors of rank 2. This is a slightly more advanced topic than previous videos, and this video is mainly intended as a small introduction to the subject. To start, we are first going to introduce the matrix notation for vectors. Starting with the vector A, we could write it as a vector with the components ax, ay, and az. In this first case, I've written it as a row vector. An alternative would be to transpose it into a column vector. In this introduction, it does not matter which version we choose for a single vector. And when we do matrix operations, we will simply correct the orientation depending on the operation we perform. For those who have taken more advanced tensor calculus classes, I'm not going to go into concepts such as co-variance and contra-variance. But in the future, if we go deeper into the topic, one can start making difference between row and column vectors. But this is too advanced here. Let us start by doing our dot product using matrices. Base the first vector as a row vector and the second vector as a column vector. Then perform a matrix multiplication between the two. This matrix multiplication will give the scalar value we used from the previous videos. Now it's time to introduce the dyadic product. This is the default operation if you write AB without any operator between them. But if you want to clarify that we're actually working with the dyadic product, we can use the symbol for it, which is a cross with a ring around it. In this course, I will always use this symbol to avoid confusion. The dyadic product is the matrix we get when we insert the first vector as a column vector and the second vector as a row vector. This will create a 3x3 matrix where all possible combinations of multiplication with the coefficients are present. The dyadic product is an example of a tensor of rank 2, as it includes both the direction of A and B. Here we can see that the dot product is the sum of the diagonal elements of the dyadic product. For the cross product, the x direction is given by the difference between these two. The y component by the difference between these two. And the z component by these two. Hence, all elements from the dyadic product are present either in the dot product or in the cross product. By further studying the cross product, we find that if the cross product is 0, the dyadic product has to be symmetric. This is a direct consequence of that the cross product contains the difference between the off-diagonal terms. If it's 0, no difference. Next up, we are going to define what happens when we take the dot product with the dyadic product, which also is the same as taking the dot product between a vector and a tensor of rank 2. Similar to the dot product for vectors, we insert the first vector as a row vector. As the dyadic product is described by a 3x3 matrix, we can insert the matrix as it is and perform a matrix multiplication between these two. Start by taking the vector multiplied by the first column. The second element will be the vector multiplied by the second column. And for the third element, we multiply by the third column. Here we can see that when we take the dot product between a vector and a tensor rank 2, we get a vector. We can simplify a bit by noting that bx is common for all the terms in the first element. Similarly, by is common in the second element and bz is common in the third element. This expression is the dot product between c and a. The same factor appears in other elements as well. And the final result is c dot a multiplied by the vector b. Hence, we can see that by taking the dot product with c and the direct product of a and b, it's the same as taking the dot product of c and a and multiplying this scalar value with the vector b. Another way we could have realized this is by inserting the matrix multiplication expression for the dyadic product. As the matrix multiplication is associative, which means that we can perform the multiplication in any order and still get the same result. It does not matter if you do the right or the left multiplication first. Let's try the same thing, but this time take the dot product between the dyadic product and the vector c. The difference is that the vector c now is on the right side of the dyadic product. We insert the matrix as it is, but this time the vector has to be a column vector to get a valid matrix operation. Multiply the first row with the column vector to get the first element. Continue with the second row for the second element. And the third row. And we got the vector as a result again. Ax is common factor in the first element. Ay is a common factor in the second element. And az in the third. This is the dot product between b and c. The same factor appears for all elements. And the final result becomes a multiplied by b dot c. Once again, we could have realized this by inserting the matrix multiplication for the dyadic product and use that matrix multiplication is associative. However, I wanted to demonstrate how to work with the matrix, as some tensors will not be written as dyadic products. I want you to note that the result is different from when we had the vector c on the left of the matrix. This means that the dot product with the tensor rank 2 is not commutative. It matters on which side of the matrix that we put the vector, unless the matrix is symmetric, which would actually give the same value in both cases. I will not talk about the cross product with dyadic products here, but it exists and it behaves in the same way, which means that it is associative and you can change the order of operations without affecting the results. Some other relationships that can be useful to know is that if we change the order of A and B, it will create the transpose matrix. The dyadic product is linear in the same way as the dot product and the cross product. With that, I will continue and try to show some examples of where we need tensors in physics. The first example is Euler's second law, which simplified can be written as the bending moment equals the time derivative of the moment of inertia I multiplied by the rotational velocity omega. Let us demonstrate this with an example. Start by writing the equation using matrix notation. If you have taken a mechanics class, you may know that the moment of inertia is calculated as the volume integral over the density times the perpendicular distance to the axis of rotation. We will assume that axis of rotation starts at origin. Assume that we apply a moment around the z-axis. This will give a rotation that we see in the animation. If we apply the same moment in the y direction, we get the following rotation. And finally apply the moment in the x direction. This time the object will spin much faster for the same moment. This is due to the difference in moment of inertia when rotating around this axis. Hence, there's something missing in our equation, as we need different moment of inertia for different directions. To make it possible to insert different values, start by inserting a unit matrix in the equation. We know that inserting a unit matrix is like multiplying with 1 and does not change anything for the equation. Multiplying a tensor with a scalar works the same way as multiplying a vector. We simply multiply each element with it. Now we can consider the moment of inertia as a diagonal tensor of rank 2. This gives us the possibility to set different values for each diagonal element. Let's update Euler's second law to write it as a tensor instead. Now we can see that we have one moment of inertia in the x direction, another in the y direction, and a third in the z direction. We can also update the inertia tensor with the expression for the moment of inertia. Ixx should be the distance to the x-axis, which is y squared plus z squared. The x-coordinate is parallel to the x-axis and does not contribute to the perpendicular distance. Similar for the Iyy term, now y is the parallel direction, hence the expression becomes x squared plus z squared. And similarly, Izz becomes x squared plus y squared. The next question, is the inertia tensor constant in time? Start by looking at the Ixx term. Then assume that we rotate around the y-axis. After 90-degree rotation, we clearly have a different value as the old Ixx value now is the Izz value. By looking at Euler's second law, we can see that the time derivative includes both I and omega. Hence, we should use the chain rule when calculating the derivative, which adds the second term with the time derivative of the inertia tensor. I will not go any deeper into this term here, just note that it exists. Finally, do we know that the inertia tensor is diagonal? The general expression will have off-diagonal terms as well. Our example will have 0 here though due to symmetry. Update the matrix with the remaining off-diagonal terms. If we were to tilt the object, we would get these off-diagonal terms. The consequence here is that if we add the moment only to the x direction, we would still introduce a motion around all three axes, and the object would be wobbling if we threw it with a rotation. Please try it for yourself, Tom. The same would apply for the y direction and the z direction as well. Finally, as an exercise, I will show the derivation of the inertia tensor. First, we need to start at the general expression for Euler's second law. This states that the moment is the time derivative of the volume integral of the density times r cross v. This general form would allow each mass particle to move with its own velocity, like it can in a fluid. Note, position vector r is the x, y, and z coordinates. Assume that the object is a fixed body. Apply what we learned in the previous video, that the rotational velocity for a fixed body is omega cross r. Then apply the back cab rule for the cross product that we also derived in the previous video. Earlier in this video, we learned that we can rewrite this as the Dyadic product dot omega. R dot r is the length squared, which is x squared plus y squared plus z squared. This is a scalar, but we saw that we can write a scalar as a diagonal matrix with its value on the diagonal. We have to add the dot product with the rotational velocity to ensure that we still get a vector at the end. Write the matrix for the dyadic product. As all operations are linear, we can place the dot product with the rotational velocity outside the parentheses. Finally, we need to subtract these two tensors, which simply is done element by element. If we use the expression for r dot r, we see that the Ixx terms are the same for both matrices. Same conclusion can be made for Iyy terms and Izz terms, and we see that we have derived the inertia tensor. This is one example where we could use the dyadic products in physics. Now it's time to move on to an example that is more solid mechanics or fluid mechanics related. That is a concept of stress and strain. Let us start by introducing the concept in a one-dimensional case. Start with a rectangular beam. This beam has length L and area A. Now we are going to pull at the ends of the beam with a force F. This will make the beam become slightly longer. Call the new length L plus delta L. The strain will now basically be the change in length delta L divided by the original length L. To introduce the stress, start by defining a cross-section covering the entire area A of the beam. The stress in this cross-section will be the force divided by the area of the cross-section. Note that the entire force will be active on the cross-section as it covers the beam. If we rotate the cross-section 90 degrees though, there will not be any force through this cross-section, as half of the force will be above and half below, when nothing goes through it. The conclusion is that the direction of the cross-section is important for the stress at the cross-section. I will come back to this later. We can also mention that the relationship between stress and strain is given by Hooke's law as a linear dependence, where E is the material constant called Young modulus. Let us study a cube instead, where we can apply the forces in any direction. To make it easier, let us only consider the two-dimensional case and introduce the strain tensor. Here we are only going to make a conceptual description of this tensor. The XX term will be when we pull on the cube with an offset of the force in the x direction, and the force is also in the x direction. This will give a similar deformation as we had for the beam. We can also add the cross-section as the dashed line. Next up is the other diagonal element, which is the YY term. Here we offset the force in the y direction, and also apply the force in the y direction. The cross-section now has changed direction as well to have its normal vector in the y direction. These two terms are relatively similar, but what about the off-diagonal terms? For the xy term, we will offset the force in the x direction, but add the force in the y direction. This will create a different kind of deformation. The cross-section will now have its normal in the x direction just as the xx term. Finally, for the yx term, offset the force in the y direction and let the force be in the x direction. This will give a similar deformation as the other off-diagonal terms. This term will have the normal vector of the cross-section in the y direction. This is the conceptual view of a strain tensor. The stress tensor is basically the force divided by area for each of these terms. More about it later. To mention a little bit more mechanics, assume that the system is at rest. The sum of all forces should be zero. If you look at the figure, this appears to be the case for each element. We also know that the bending moment for each element should be zero. This is not the case for off-diagonal elements. With these forces, they will start to rotate. Hence, something is missing. To balance the system, we need to add the force with the opposite bending moment. This would change the deformation to look something like this. We can repeat the same for the other off-diagonal term. In physics, the strain tensor has to be symmetric, otherwise the cube would start to rotate. This will be important later when we study fluid mechanics. The same will apply for the corresponding stress tensor, as the stress tensor basically is the force, while the strain tensor is the deformation. And we have symmetric forces in the figure. A tensor of rank 2 should have two directions. Which are the two in this particular case? Let us illustrate it for a circle where we more freely can change the angles. Add 2 points where we apply a force in the opposite direction. Draw a cross-section perpendicular to the points to ensure that the full force passes through the cross-section. Add the normal direction to the cross-section. Our first direction will be the offset between the points, which is the same as the direction of the normal vector. Our second direction will be the direction of the force vector. And we have two directions we can vary, hence a tensor of rank 2. Let us continue to talk a bit more about the stress tensor. Start with the XX term. As stress is force per unit area, the stress is distributed over the entire area. Here we can add in the cross-section with its normal vector. When we draw the stress distributed, it's easy to understand why all the force passes through the cross-section in this case, but not when we rotate it 90 degrees. To simplify the drawing, only keep one arrow. The XY term is when we apply the force in the Y direction while keeping the offset in the X direction. The YX term is when we apply the force in the X direction but with the offset in the Y direction. And the YY term is when both the force and the offset are in the Y direction. This means that if you have the cross-section in X direction, these stress terms will give the force. And when we have the cross-section in the Y direction, it is these terms that give the force. If we put the cross-section on the diagonal, all terms would contribute to the force. The final question is, how do we calculate the force? Start from the expression for the stress. Convert this into a vector equation by adding the normal direction and take the dot product with the stress tensor. Let us write it on matrix form. Start with the n hat x term, which will give the contribution from these terms. Continue with the n hat y term, which gives the contribution from these. Both expressions add force in both x and y direction. Here we see that if we need to calculate the force and know the stress tensor, we can use our matrix algebra to handle the stress tensor calculations. This final video in the first block covered a bit more physics than the rest, but this is because I think these concepts can be new to many watching this, and we'll see them again if you study fluid mechanics. In the next block of this course, we'll talk about the derivative. We will see some tensors there again, mainly when we take the gradient of a vector. Thank you for following the first block in the series.